This lesson is on optimization, section 3 of unit 5. So what exactly do we mean by optimization? Merriam-Webster describes optimization as an act, process, or methodology of making something, such as a design, system, or decision, as fully perfect, functional, or effective as possible. Specifically, the mathematical procedures, such as finding the maximum of a function, involved in this. Okay, so I think that second part of the definition is the one that we have to take and be focused on here, that it's the mathematical processes, such as finding the maximum of a function, involved in this. So let's look at a typical example. You have a sheet of cardboard that is 14 by 30 inches. With it, you hope to make an open-top box. You do this by cutting out squares of equal size from each of the four corners so that the four sides can be bent upwards. What size should the squares be in order to create a box with the largest possible volume? So let's start out with what we've got here. Basically, we've got a sheet of cardboard that's 14 inches by 30 inches, a flat sheet. Now we want to cut squares out of each of the corners, okay? So that from each corner, we're going to cut out a little square. Now all the squares are going to be equal in size, and then we're going to take the sides and bend them up, fold them up, to create an open-top box. Now, as I said, each of these is a square, and we don't know what that value is. So we're just going, for now, call it x by x, all right? So as you can see, we're going to have four squares that are x by x. So once we cut these squares out, we're going to have the sides of our box be 30 minus 2x for the length, and 4 minus 2x for the width, since we're cutting out these squares, which are x by x. Now we want to find volume. So what is volume of a box equal to? The formula for volume is length times width times height. Now, if we relate that to our diagram, we can see that the length is 30 minus 2x, the width is 14 minus 2x, and the height is simply x. So there's our volume in terms of x. So if we multiply everything out, we end up with the volume is equal to 420x minus 88x squared plus 4x cubed. Now this is what we want to maximize. We want to maximize the volume. Now in order to maximize the volume, we're simply going to take the derivative of our volume function. So we want to know dv dx. And if we look at our function here, and take the derivative of it, we end up with 420 minus 88 times 2, which is 176x, plus 4 times 3, which is 12x squared. So there's our dv dx. Now we're going to take that first derivative, and we're going to set it equal to 0 to look for critical points. All right, so I'm going to rewrite this first of all, rearrange this so it ends up being 12x squared minus 176x plus 420, and we set that equal to 0. Now, we got a common factor here, so I can divide everything through by 4. If I divide everything through by 4, I end up with 3x squared minus 44x plus 105 equals 0. Now, if I take that and factor it, now, I can factor it, or I could take and graph this on a graphing utility, and I would find that this would equal 0 when x is equal to 3, and when x is equal to 11 and 2/3, or 11.67. Now, if we look at these two answers, we realize that x cannot equal 11.67. The reason it cannot equal 11.67 is because the width is 14 minus 2x. Well, 2 times x in this case would be 22 something, 23 something actually. 14 minus 23, that would make the width negative. So 11.67 is not a valid answer. X equals 3 is a valid answer, and therefore the squares are going to be 3 by 3. Now, based on this example, let's look to see if we can come up with steps to take and solve optimization problems. And these steps aren't that different from solving any word problem in math. The first is basically to draw a picture. I strongly encourage you to draw a picture so you can see what you're doing. And identify the known and unknown quantities. In other words, you want to know the constants and the variables, thinking of the known and unknown. The next step is to write an equation, or you might say model, that will be optimized. So write an equation that will be optimized. And this is basically your modeling part. Make sure the equation is in terms of a single variable, all right? So in the previous example, we had volume, and it was only in terms of x, okay? We didn't have two unknowns on the right side of the equal sign. We only had one. Step 3 is to determine the desired max or min values using calculus techniques. In other words, take the first derivative, set it equal to 0 to find critical points. And then the last step is to determine the domain endpoints of your equation to verify if the endpoints represent a max or a min. Okay, with this also, in our previous example, we had to look to see which answers were valid and which were not. Those that were not resulted in negative distances, things like that. So you also want to see if the endpoints verify or represent a max or a min. And this is basically the steps you follow for any optimization problem.